Speak of yet another exciting quantum PCP talk for the quantum PCP day, quantum Hamiltonian complexity day. Tina from MIT will tell us about a new gap amplification procedure. And yeah.
Thanks. Yeah, so thanks for being here. I am going to talk about a new quantum gap amplification procedure. This is joint work with Tiago, Tony, and Tamar. So obviously the question that we're trying to address here is the quantum PCP conjecture. So just to remind everyone, I assume everyone has seen this before, but okay, what is it? We want to conjecture that there is a family of Hamiltonians, and I'm going to write it like that on this side and probably never again. So, it's a family which is indexed by natural numbers, n. Each, member of the family consists of like the Hamiltonian and then like two parameters, alpha and beta. And we want the following conditions. Beta minus alpha is a constant, okay? The Hamiltonian is local, so its locality is constant. It's supposed to have polynomially many terms as well. That's automatic if you assume that all the terms come from like some fixed set, all the like constantly large terms come from some fixed set. And finally, deciding if the ground energy of the Hamiltonian is less than alpha or greater than beta should be QMA-hard. So that's the conjecture.
So, sorry, wouldn't you need the Hamiltonians to also depend on an input, not just on n?
Do they need to? Oh, yeah, sure. Okay.
Yeah.
Yeah. Okay. Yeah. Okay. But presumably, okay. If I screwed it up, you can fill it in because it's.
We do know what the
Okay. So how would we try and prove that? So, one sort of natural way to try, I mean, in quantum, we're not very original, right? So we always just like look at what classical people did and then copy it. So we can try to imitate proofs of the classical PCP theorem. So there are kind of like two major lines of proof. The first one is the algebraic proof, which relies heavily on these like, algebraic codes. And I guess the consensus there is that this approach is mostly dead quantumly because you don't have these properties quantumly. Like quantum codes have very different behavior from classical codes. The second approach is the combinatorial approach, which was initiated by Dinur in 2007. And I guess this one has been considered to be a better guide because it sort of conceptually makes clearer what exactly is needed for the PCP theorem to be true. And in particular, there are these two main ingredients that she uses called gap amplification and alpha bit reduction. So I'll talk a little bit about what those are, so that then we can look at how maybe we could quantize them, right? Okay, so in particular, obviously, I'm mostly going to focus on gap amplification. I'll say like 2 words about alpha bit reduction. So gap amplification is we start with some Hamiltonian family. And then let's just assume for the simplicity that a Hamiltonian family, I'm going to say it in the quantum language. And for classical, you're just supposed to imagine that like all the terms are, like the Hamiltonian is a classical CSP instead of a Hamiltonian. So we start with a Hamiltonian family. Let's imagine for simplicity that every Hamiltonian is going to be a sum of m terms. M is a function of n. But I'm going to suppress the n dependence from now on. And let's say it has, it's a sum of projectors. So it's a sum of m projectors pi I. And all of the terms have constant locality on qubits, okay? So gap amplification is a procedure that would take such a thing and map it to a new Hamiltonian family where alpha, so the family also includes these parameters alpha and beta, and we assume that we begin with like beta minus alpha is 1 over poly, because that's the regime which Kitaev's circuit Hamiltonian reduction shows is QMA complete. So okay, what happens? I'm also going to assume here that alpha is like exponentially close to 0, and beta is 1 over poly. That's the regime we're looking at. This is all just like basically without loss of generality, but for simplicity. Gap amplification basically is going to take alpha is going to remain almost unchanged. Beta is going to go to t times beta for some constant t, okay? And the Hamiltonian will change slightly. Now it will have d to the d times m many terms for some large constant d, and for the same like amplification parameter t. And it will have the same locality, but now on qubits. So the dimension of the variables which you have is no longer 2, it's going to be very big. It's going to be this d prime, which is d to the big D to the t. Okay, so basically it like becomes, you know, it goes from d originally, it was 2 originally, and now it becomes like 2 to the 1,000 or something like this. Okay. So that's gap amplification, and you should think of this as intuitively, it basically like takes a Hamiltonian, and then it like blows up the promised gap and tries to keep all the other parameters as stable as possible. If you have such a parameter, like if you have such a procedure and then you just keep doing it, eventually you'll get from the regime of 1 over poly gap to like constant gap. And that was the conjecture that we're aiming for, right? That constant gap Hamiltonians are QMA complete. Yes.
So if you want to do this thing for L greater than 2, would you have to reduce to 2 anyway? Like, does Dinur's procedure work for any L, or actually
I think it works for any L.
For any. Okay.
I'm not super sure about that. I think it will. So, okay. So that's what Dinur's getting as parameters. And the main problem is that you have these, okay, the main parameter you fail to preserve here. So like the, okay, my cursor doesn't show up, I guess. That is not very useful. Okay, so this is fine, because if you do this log, okay, so the idea is we're gonna do this log many times, basically. That's the regime you should keep in mind. If you do this log many times, like you repeat it log many times, this is still a constant. This is a constant. So you'll amplify from 1 over poly to constant. This is also a constant, like there's some large constant to the t, which is a constant. So this is going to be like poly times m, which is fine. Like it still has polynomially many times, right? This is good, we didn't change the locality. This is bad, like if you do this log many times, this is gonna be enormous, right? So basically what she does is she does this and then she fixes this part using this thing called alphabet reduction, which we have no idea how to imitate quantumly. But it turns out that for her, getting this in her gap amplification is good enough because she could fix this.
What's small d here?
Small d is the dimension of the variables. So originally it was 2, I said it was qubits, and now it's going to be like this d prime. Yeah. Cool. Okay. So any questions about the Dinur setting before I move on? Okay. So that was Dinur's setting. Here are our parameters. Also the parameters of this work by Aharonov, Arad, Landau, and Vazirani, who did like some similar thing many years ago. These are worse parameters, and I'll explain why in a second. So it's also simpler. It's like, okay, the amplification amount is the same. The change comes in how much the Hamiltonian changes when you amplify by 1 round. So we'll go from, so the number of terms is also the same. But now we don't get the same locality control. So Dinur did not change the locality when she amplified, right? We do. It becomes from L, it becomes T times L, right? So we amplified the locality by the same amount that we have amplified the gap, more or less. And okay, we don't get the alphabet blow up, but that's actually bad. Like you want the locality blow up if it happens to go in the alphabet, because it's much harder to fix if you've just like blown up the locality without control than if you've blown it up by making the variables bigger. Okay, that's the intuition. Okay, so what does this mean just in terms of how do we stand in terms of trying to prove quantum PCP? So what we achieve and also what AALV achieve can be considered sort of a quantum analog of, if you know the classical literature, sequential repetition. And what Dinur needs is parallel repetition. So there is a strong intuition that gap amplification without the locality control is not good enough to at least to instantiate Dinur's template of how to prove PCP. On the other hand, there are like no-go theorems for matching Dinur's template. Like you cannot get parallel repetition provably in the quantum setting, at least not with like the classical parameters. And this is by Brandau and Harrow. I forgot what year that was, maybe like 2013 or something. And okay, apart from all that, all the problems with gap amplification, which is like the first step in Dinur's template, also the current directions for alphabet reduction don't match Dinur's alphabet reduction, like classical alphabet reduction, even in the best possible case. So there's a long way to go before we could possibly even like attempt quantum PCP, but I don't think it's hopeless. And okay, I think that these are all good reasons that you should just like try and prove anything that you can, right? Because right now we have no idea what might be a fruitful direction. So, okay, let me say a few words. Firstly, about Brandau-Harrow, for those of you who may be wondering, like, okay, Brandau-Harrow is basically, it proves certain no-goes against gap amplification in the quantum setting. We get around these no-goes precisely because we don't control the locality. So it's not like a super exciting way that we somehow manage to subvert it. It's just that we don't, like, their result does not apply to our thing. Also because our thing is not like the sort of thing that Dinur would want in her template, okay? And okay, I will also be very upfront that we have no good reason that there's no particularly compelling application that we find from this result. That cannot obviously, or like, it is obvious that it cannot be known from like previous techniques. But, you know, we have to do some non-trivial work to prove it. We have to make new techniques compared with the existing works that could possibly recover like the same applications that we talk about. So I think it's still, you know, worth thinking about. And in particular, this will become clearer, like what I mean when I talk more about like AALV. So, okay. Let me talk now about how do you actually do this? How do you achieve the parameters that I talked about? How do you amplify the promise gap of a Hamiltonian family, right? So here are two sort of natural approaches that you might try. Let's say set the amount of amplification that you want to be a constant, right? So option one is product amplification. So you take your Hamiltonian H and you map it to identity minus H to the T. And that product there is just like a little matrix product, okay? So that's sort of like intuitively you should think of that as like, if your Hamiltonian is a sum of projectors, then what you're basically doing is taking the original terms and then like picking T uniformly random ones and calling your new constraint like the AND of all the T old constraints that you picked. That is basically what product amplification should be. Like if you think about it classically, that's the intuitive analog. And that's because if you take the product of projectors, it's equivalent to basically to doing the AND over those projectors, like taking somehow the, like, it's not quite the same, but like the subspace that they all like share in common, basically. It's something like that. Okay, and then option two is tensor product amplification. So it's exactly the same, but now you have the tensor product instead of the product in the exponent. And this is, okay, it's very similar, but now instead of like taking T random terms from your original Hamiltonian and then measuring them all on the same system and then taking the AND, you're sort of taking, you know, you're making T copies of your original system and then measuring one term on each, basically, and taking the AND across these systems. Okay? Questions about that? Okay.
So this option two would not match the parameters you displayed earlier, right? Because I think there should be an extra factor of n. Oh,
extra factor of n, where?
Because you're taking many copies in these estimates that you wrote, right?
Yeah.
But here you're not fixing the number of qubits to be.
No. Yeah, I said nothing about the number of qubits. Yeah.
Okay.
Yeah, the second option does increase the number of qubits, but not like, you know, untenably. So, okay. So if I write it out formally, this is what you see. So if I assume that my original Hamiltonian was a sum of projections, which is what you see on the left here, like this, then after you product amplify, you get this. So I just like took that and expanded it, basically, okay? And same with tensor product, except now instead of like this is a product here, this is a tensor product, right? And what you see here is that you have sort of m to the t terms in either of these amplifications. where m is the original number of terms in the original Hamiltonian, because you just sort of like picked, t terms uniformly at random. The number of possibilities you have now is like m to the t. And okay, randomness here translates to like picking, it's like uniform over all of the possible terms. So, another way of saying like the usual verification algorithm is to pick a random term from your Hamiltonian and measure that. So if I quantify over all the randomness, I'm basically just like writing down all the possible, combinations of m of t terms from the original Hamiltonian. Okay, so to get the parameters that I talked about earlier, I want fewer terms than this, right? M to the t is too many. I want like, m times a constant, where in particular the constant was d to the t for some constant, right? So one way you can do this, and this is what AALV achieve in their paper, is that you subsample the terms. So you had m to the t terms. Oh, I want less terms. Why don't I just delete some? Okay. Now, obviously, now you have to like analyze it to say that actually this also blows up the gap by the same amount, or roughly the same amount, right? Because if you just delete arbitrarily, then maybe you completely destroy the gap, right? So it requires some analysis to show that this works still as gap amplification procedure. And I should say that this like sort of de-randomization or subsampling is exactly how Dinur does it as well, but she also does other stuff on top of that. So this is like one part of Dinur's gap amplification. How do they achieve this? It's a technique called the detectability lemma. It's very powerful, actually. I don't know how, if they like, maybe Umesh can say, like if they knew how, interesting and how many applications it would have when they made the result, but it has had many applications and has proved many very interesting things, like things about area laws and things like that, right? Okay. So the message here is, okay, you have too many terms, delete some, and then prove that you didn't change the amplification amount by too much. And okay, basically what we do is we do the same, but for tensor product amplification. So the original thing, the detectability lemma is sort of uniquely adapted to analyzing the product case, more or less. To analyze the tensor product case, you kind of need new ideas. And that's what we come up with. We got the same number of terms, like it's almost the same, but in terms of parameters. But we use a new technique, which I guess I called Mises de Finetti. And then there might be some like minor improvements over AALV. Like for example, they have this like constant locality requirement for the original Hamiltonian. So their Hamiltonian must start with constant locality, which means that they cannot iterate their procedure without also doing locality reduction, which we do not know how to do in the quantum case. We can iterate it without because we don't have this requirement, but I think it's not actually clear to me, at least, that like you cannot just fix their proof using the more modern techniques that now exist to not have the constant locality requirement. So yeah, okay. But the message is like, okay, we're achieving something very similar to them, but in the tensor product case, and this requires a new technique. And since like their technique had so many cool applications, one could hope that somehow this would be useful to look at. Questions? Okay. Okay, so now let me tell you, this is sort of self-contained, by the way. I'll try and tell you about the main technique that we're developing here. And this part, in case you completely did not follow the earlier part, this part is self-contained. And in particular, I will not try to like sketch the whole proof for you. I'll just try and say like the technique. And so the technique is based on this thing called a de Finetti theorem. And okay, this is somewhat interesting maybe to people who know the literature because de Finetti theorems were used previously also in the context of quantum-PCP, but they were used precisely by Brandau-Harrow for their no-go result. And here we're using it to show like a go result, like a positive result. So I guess it's a versatile thing. Okay, so what is a de Finetti theorem? Let psi be any permutation invariant pure state in the symmetric subspace. So permutation invariant just means that you should think of psi as having like several like registers, And if I swap two of them, any two of them, psi should remain exactly the same. That's what permutation invariant means. Symmetric subspace is like, somehow the span of all the states that are like this, that are permutation invariant. And okay, we have some parameters here. So D is going to be here the dimension of each register. And T is going to be, okay, T and K are both parameters that quantify how many of these registers there are. But why are T and K different? It's because Finetti basically says, so if you have such a permutation invariant state, and then you throw away some of the registers, the remaining registers are actually approximately in a convex combination of almost product states. Okay, so this is very useful because it means that if you are in a situation, as we are, in trying to analyze gap amplification, where having a product state would be really convenient, because then you could just analyze it almost classically, right? The main problem, in fact, when you analyze gap amplification is that you have possibly entangled ground states, right? So if you're in a situation where you kind of want a product state to exist, but you don't see how to make it happen, what you could try is just throw away some of the registers of your state. First, make sure your state is permutation invariant. You can do that sometimes using various tricks, and then throw away some of the states, and then the rest should be actually almost product, a convex combination of almost product states. And so K is going to be the amount that we throw away here, and T is going to be the amount that we leave. That's not like the T is, you're supposed to identify it by the amount that we're amplifying, or the number of copies that we're going to take.
Sorry, so we're imagining K is large compared to T, or they're both large?
Right, so I will, that's exactly what I'm going to say next. So T needs to be large relative, K needs to be large relative to T for this to work, In particular, usually it also needs to be large relative to D, or rather to log D. So usually you want T and K to be comparable, and also you want D to be, log D to be comparable to K. Otherwise, you're never going to get anything. You need to throw away quite a lot of your system, and also, intuitively, you can imagine if the systems are really the registers are really huge, and you throw away two of them, it's not going to, So T and D need to be smallish relative to K for this theorem to work out. So as I said, this is great because if the ground state of the amplified Hamiltonian were magically product, then derandomized tensor amplification, which is what we're trying to analyze, would be much easier. Unfortunately, as we said, K needs to be pretty big relative to log D in order for the parameters to be good in this approx here. If this approx is trivial if K is too small, right? Okay, let's just briefly say what that actually means. So log D, you should expect to be about poly, the instance size of the Hamiltonian. Because D is the dimension of the registers, and for quantum registers, that's exponential, right? So then if you take log, you get a polynomial back, and you want T to be a constant, right? So that means, okay, you want T and K both to be sort of constant because you don't want to blow up the system size by too much when you do amplification. And so that's just not going to work. You can't make the number of new systems constant and also require it to be larger than log D. Okay? So that's the main reason you can't just black box apply Finetti. And okay, to tell you how we get around this, I need to tell you sort of sketch a proof of a Finetti theorem, and then I'll tell you why we can improve on that proof to get better parameters in our particular setting. So here is a very short proof of a particular Finetti theorem due to Vidic and Yuan in 2016. It consists of two facts, which one needs to prove, but which are pretty elementary. Fact one is sort of a characterization of the trace-out operation. So it says that for any permutation invariant state in the symmetric subspace, if you trace out the last K registers of that state, this is equivalent to doing this. Okay, let me say what is happening here. So here's the state in the middle. Basically, what is happening here, you're projecting the last k registers on a particular pure state. Okay, so the integrand is like, you project this guy onto a particular pure state phi at repeated k times, phi tensor k. Okay, so it's just like literally one register pure state and then like copied k times. Yes, yeah.
The interval variable.
Oh yes, I'm sorry. Yeah, that was a mistake. Okay, yeah. This is a typo. It should be phi. Or phi. Okay. And then we're integrating over all possible one system phi. So basically all possible instantiations of this state. And this is a measure. It should be d phi, but it means the Haar measure. So the Haar measure over all one system states. And then you project this original state you project the last k registers onto k copies of phi. What this basically means is that you can consider the tracing out operation for a symmetric, like a permutation invariant state, to actually just be equivalent to like projecting the last k registers into like some random state. Some random state, k copies of some random state, basically is what it's saying. And okay, why would you ever want that? The reason is fact 2, which is sort of the measurement statistics lemma, and I'll explain why in a second. So fact 2 says that for any permutation invariant psi and any pure one system state phi, tracing out the last k registers, projecting psi into k copies of phi on the last k registers, and then tracing out the last k registers should actually leave you with like t copies of phi on the remaining registers. So remember, psi was t plus k copies, right? Or t plus k registers. If you take the last k registers and project them, so just post-select on getting phi to the k, then the other registers should look like phi to the t. This one is much more remarkable than this one, and also harder to prove. I think I said that in the next slide. Yeah.
Sorry, I'm a little confused by the second to last line. Like, aren't you like contracting by 5 times 3k? Isn't that already the, like, what are the dimensions here? Like, how do you trace that once you've already contracted them?
Oh, here I just projected, right? I didn't actually contract yet. Like this thing is a projection of the last registers into phi tensor k, right? And then I like got rid of it.
I think it would be a projection if you had like a cat bra.
Or maybe I missed.
You're like sandwiching, you're like reducing the dimension of the expression, and like you've already gotten rid of those registers.
Okay, I guess.
It's not.
Okay, I think this maybe then should be a cat bra. Yeah.
Okay.
Yeah. Sorry. Okay, it should be, or I guess I could just get rid of the trace, right? Yeah, that would be another option. Okay. Okay.
And is this an additive error?
The approx or?
Yeah.
Yes, it's an additive error. There's also like the approx also hides like certain registers will not be in any particular it will not be like actually this will be like this with some registers completely corrupted, and then the rest will be close up to additive error.
There will be some unknown factor like the factor before the final expression, right?
Yes, because this is like an auto trace preserving. Yeah. Okay, ignore the trace last k on the last expression. Yeah. But intuitively, these two facts together give you a de Finetti theorem, because this one says that tracing out the last k is actually equivalent to just like projecting and then projecting onto a random state. And this says that if you project onto any state of the form phi tensor k, then the rest should look like a product state, basically, like that state times t, right? So if you plug it into here, this thing will collapse to like phi tensor t, right? And then this will be your convex combination that you were looking for. That's how you prove the de Finetti theorem.
Yeah. Is like for worst case states, like for any psi and for any pure state phi?
Yeah, I think so.
Oh, it just feels like if I think of phi as 0, and then my permutation invariant state is like all permutations of like k zeros and t ones.
Yeah.
Then once I contract by 0, don't I just get like only the ones left?
Yeah, you'll have factor of 0 before the.
Sorry.
You'll have factor of 0 before the final.
Oh.
It's like that the factor will be like the probability of this
That's happening. Yeah.
Oh, okay.
Yeah, sorry. Like I'm suppressing a lot in the approx.
Okay.
Yeah. But okay, that's supposed to be in the intuition for the Finetti theorem. And fact 2, let me give like another intuition for it. You're supposed to think of it as like you're taking measurement statistics about psi. So somehow you're like looking at the last k registers of psi, which, okay, for a permutation invariant state, it doesn't matter, right? The last k registers is equivalent to any other k, equivalent to a random k. So you should imagine yourself looking at like measuring a random k registers of psi, and then finding that actually those k registers happen to be in the states phi tensor k. And if that's the case, then because the state is permutation invariant, you sort of conclude that actually the remaining state must also be in like copies of phi. That's the intuition. Yeah. Okay. So the reason why, yeah, okay. So fact 2 is the main reason you need k to be really large relative to log d, because, and this is like, you can see this intuitively by thinking about the reason, which is unless you measure like a really large number of auxiliary systems to like, if you look at a large number of systems of psi and find that they're all like this projection, this projection here is intuitively really, really unlikely to happen, right? So you can only conclude that like the remaining systems are in the state phi tensor t if you look at a really large number of systems and say that they're all in like copies of phi. That's why k needs to be large. So intuitively, you need to collect a lot of measurement statistics about your state in order to say anything about the leftover stuff using the permutation invariance, right? Okay. So that's the barrier for why you can't just use Finetti in order to do it. And the question that led us to be able to like get around this is that, like, do you actually need to know so much about the state? So this Finetti theorem tells you that like the remaining state, once you've looked at your k registers and found that they're all in like copies, the remaining system is product. Like that's very strong, right? Do we actually need such a strong characterization of the state in order to be able to do an analysis? And the answer is no. So let's see, some time. Okay. So let me do a mild digression just to like tell you how we're actually, a little bit about our proof. So you have context for why we're using the Finetti theorem and why the simplification that we make is good enough. So our overall proof approach is to try and characterize the mean and the variance of a quantity called the violation number, which Dinur also uses. So the violation number is basically just, you pick some random constraints, like this is, you're supposed to imagine like this is your T systems that you made copies of to do your amplification. And you pick random constraints, so like T of them. And then you check individually, like you measure each one individually on a different copy, and then you see which ones are violated. So here, like red is violated and green is fine, right? So here, like n is 1, basically. Obviously, there's like, in the quantum case, actually, there are like traces involved, but let's just pretend that they're all like either completely violated or not. Like the trace is 1 or 0, okay? Okay, I said randomly. How do you actually pick the constraints? You're supposed to imagine that you pick them pairwise independently from among the constraints of the original Hamiltonian. So why pairwise independently? Well, Dinur uses random walks. A very like false intuition is that random walks are kind of pairwise independent if you do them for long enough. Now T is like not nearly large enough for that to be true here. Like it's got a constant, you need like a log step random walk for it to be close to pairwise independent. But actually, Tiago came up with like a very clever way to reduce the random walk case to the pairwise independent case. So we'll just consider the pairwise independent case for now. So this is modeled after Dinur's analysis. As I said, she also considers this violation number, but classically. And we're trying to do it quantumly. So, okay, why did I tell you this? So it turns out the mean of this thing is easy to characterize. The variance is the hard part. And because of pairwise independence, the variance of that number n, that measurement n, actually turns out to look like this. So it's a sum over all registers, like pairs of registers, ij. And then you take the trace of the original Hamiltonian on register I, tensor with the original Hamiltonian on register J, on the ground state of the amplified Hamiltonian. So the prover hands you some ground state. It has T registers, but you have no idea if it's product or not, right? It could be not. And then you are going to measure the original Hamiltonian on one register, and then picked at random, let's say, and then the original Hamiltonian on another register. Also, I and J are picked at random because we're summing over all of them. And then you're going to say, what is the trace of this? Like, obviously, if rho were like also respecting the product structure, then it would be easy. It would just be like, trace of H rho squared, right? That's what you want. Like that would make the analysis go through. Rho may not be product, and that's what we have to deal with, right? So, okay, how are we going to deal with that? We're going to try and do de Finetti, but we don't have enough space to do like real de Finetti, so what do we do? So here is what we do. The first observation is that actually classical de Finetti suffices for us. Because the eigenbasis measurement of like this operator H tensor H on all of the registers of rho commutes with the measurement whose trace against rho we want to bound. So the trace, we want to bound like the trace of this guy, Hi tensor Hj, on rho, right? So the observation is basically, actually, you could just like measure rho in an eigenbasis, like a tensor product eigenbasis of H, and get like a classical distribution and do your whole analysis on the classical distribution. This commutes with Hi tensor Hj, no matter where I and J are, right? So basically, you don't actually need to consider quantum states at all. Basically, in this case, you can just get away with considering classical distributions. Okay, and then the second observation is this is not actually good enough because classical de Finetti, like it has the same bad scaling with sort of, instead of the dimension of the systems that you're swapping around, it's the alphabet size of the like distributions that you're swapping around. So classical de Finetti deals with like, you have some permutation invariant distribution, classical distribution. So it's like, some random variable that's split into registers and it's supposed to be swap invariant on those registers. And there's like some alphabet over which each register ranges. It has bad dependence on the alphabet. So if we like, okay, this eigenspectrum probably has a lot of eigenvalues, right? If you just did the eigenvalue measurement, you'd have a very large alphabet size for your classical de Finetti, and that would also be bad. But actually, for our analysis, we don't actually need a very good characterization of the energy. Like for us, like a very coarse-grained characterization is good enough, which is just going to be, is it big or is it small? Like we only need a binary measurement on each register to tell us, is the energy big or is it small on this register? So basically, this alphabet size reduction is actually how we're able to get around the issue we had earlier that for de Finetti to apply, you need like K to be, you need the number of systems that you trace out to be really large. Questions? Okay, so at this point, you actually have a new problem. So if all the de Finetti parameters are constant, then the de Finetti error is never going to be smaller than a constant. It could be a small constant, but it's going to be a constant. And you want this gap amplification procedure to work even when the ground energy is like 1/poly. So at this point, in that regime, you have a new problem because like the de Finetti error that you're getting is like dwarfing the amount, like the actual ground state energy. And so you're not going to get very good amplification because you're just going to get stuck. Every time like you try, okay, it's supposed to like go from like 1/poly to like 2 times 1/poly. And you're just going to like get this massive error of constant that could just push you back down, right?
So
yeah.
The error would also depend on the number of copies, right? That's not a constant.
Wait, sorry, say again?
The error would also depend on the number of copies, right? But that's not a constant.
The number of copies is a constant here, right? The number of copies is T, which is our amplification parameter.
Oh, so you're saying 1/T is not enough?
Yeah, 1/T is not good enough, yeah.
Okay.
Yeah. Even e to the minus T is not good enough. Like anything involving T only is not good enough.
Right.
Yeah.
My language.
Yeah. 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 So, okay, that's a problem. The way we sort of get around that, I won't go into it because it's more tailored to what we particularly do in our proof. It's less standalone, but like the way we get around it basically to observe that you can in some, like, okay, I was talking about these quantities as if the error was like an additive error, right? I said like, you know, e to the minus t is never going to be good enough because it's going to add on top of your Hamiltonian energy, right? You could also imagine, okay, what if you had like a relative error? Like if it was like Hamiltonian energy and then like times e to the minus t, that's fine, right? You have to like do some tricks in order to make it a relative error rather than an additive error is basically how we fix this. Okay, so that was the technical part. When we say the applications part, which is going to be very easy to follow because there are none. So the one we advertise is this so-called streaming quantum-PCP. So it's basically like imagine it's basically the QPCP conjecture, except that the terms are not local, which of course is like silly because okay, if that was all, like you could get it very easily, right? You could just like make your one non-local term just be like measure a QMA verification cycle, done, right? Okay, why is it non-trivial? Because our terms, you can get this by repeating our thing, our gap amplification procedure log many times, just as Dinur does it. We don't have alpha bit reduction, so we don't do that. Just like don't forget about it. So okay, you don't control the locality because we can't, right? But you have all the other conditions of the QPCP theorem. So you have polynomial mean terms, you have a constant gap, and the terms are not local, but they're kind of nice because they are tensor products of local terms. So each term is just like a tensor product of like 5 local terms or something. And okay, that's nice. We call it streaming because you can imagine measuring this with like very limited quantum resources, and you would just need to like you would measure all the tensor product terms individually, and then you just like collate them using an AND, basically, a classical AND. So this can be done using like log memory, let's say, classically. So that's why we call it streaming. Like you can look at the qubits sort of one at a time or constantly many at a time and manage to measure the terms. It's not clear that you can't get this via other means, as Anurag told me. But okay, that's what we say the application is. There are some other applications. Okay, I think there's like a missing. Yeah, okay, no, actually it's fine. So another application that we have is you can sort of prove a locality gap trade-off with this theorem. So if you have a Hamiltonian with gap epsilon, let's say, and locality L, then you can convert it using our gap amplification to a Hamiltonian with gap constant and locality L times 1 over epsilon. So basically you like shove the locality, you shove the gap into the locality. Like for example, if you had like what people call weak PCP, like Hamiltonian with 1 over polylog gap and locality polylog, we could then immediately get a Hamiltonian with constant gap and locality still polylog. So again, it's not clear to me totally that like this cannot be achieved using other means like ALV, for example, if you just fix like the constant locality thing, but okay. Okay, possible application, there's this conjecture called the games PCP conjecture, which is a necessary consequence of Hamiltonian PCP. It basically says that the conjecture says that there exists like a MIP star proof system, a non-local game with, let's say, polylog question size and answer size, and efficient provers that is QMA complete to decide whether the value of the game is large or small. So this result of ours, I think, genuinely is the only way you could get right now the question size of this of such a game to be logarithmically large under like normal deterministic reductions. But unfortunately, like our result does not help with answer reduction. So you could use it for question reduction in this setting, but answer reduction is still an open problem, so we do not solve game PCP. So that's an open question. There's also sparse PCP, which is the same as normal Hamiltonian PCP, except that you ask, instead of the terms being local, you ask that they're sparse. So in some basis, you can write them in a way such that the whole matrix, it's like a giant, exponentially large matrix, but each row and each column only has polynomially many non-zero entries. And local Hamiltonians are always sparse. Oh, and it also always has to be in the same basis. So you pick one basis and then all your terms have to look sparse in that basis. So local Hamiltonians are always sparse. So again, sparse PCP is like a necessary consequence of Hamiltonian PCP. Okay, like maybe you would hope that somehow our result would help with this, because our result kind of says that you can make a Hamiltonian that's QMA complete with constant gap that has these polynomially many terms that are sort of like nice, right? They're like tensor product. So if you could come up with some sparsification algorithm that like relies on the tensor product structure to get it, I think like generic sparsification will not be good enough. But if you could somehow sparsify each term individually using its tensor product structure, then if you add them all up, you'll like each one is sparse on its own and you only have polynomially many, so the sparsity will still be polynomial. So that's, another direction. We didn't manage to figure out how to do it, but, it's an open question. And if you can somehow think of any applications of this result, please let us know. Okay, that's all. Thank you.
Thanks, for the great talk. Questions? Okay, so I'll start with the first one, Alvin.
This might be arbitrary, but like, do you ever thought about any connection to these so-called Kikuchi methods in
What method, sorry?
Kikuchi method?
Oh, I don't know this.
Anyway, but like it seems like when people see classical CSP, they also try to produce copies, and someone introduces many-body Hamiltonian, and they say that somehow if you introduce lots of copies, the mean field solution would somehow get pushed, like the spectrum got pushed in some way. But it sounds vaguely related.
Okay, maybe someone with more physics can answer this question. I don't actually, I've never heard of this, so yeah. I think in the CS context, one would say this is a sequential repetition result. So. If you want to answer the question.
Oh yeah, I was instructed to ask a question by Chinmai, who's not here.
But he's watching the live stream.
Over to Natalie.
Okay, good.
Oh, sorry, someone else was there. Wait, there was someone else who raised a hand on this side. Yes.
Yeah, so if you take the classical Finetti theorem, do you know whether it has similar applications? It sounds like the style of what you did may be useful for direct product testing or something.
You're asking if somehow this style of like doing the proof could, yeah, it would work if it was classical. But I think there are already like better classical analyses of this sort of thing. Yeah, so I don't think you would get anything. I mean, I don't know. I haven't checked. I don't think you'd get anything like new beyond what classical people already know by applying this kind of thing. It's because the techniques are sort of quantum friendly that anything is special in the quantum case.
So we'll just let Chinmay answer the question. Then we'll get. So Chinmay, you can ask your question. Oh, you sure, go ahead.
Okay, the question is, do you, Tina, believe that ground states of QPCP Hamiltonians will be tensor products with ground states of the original Hamiltonian, maybe after some permutation of the qubits, or will it be something more complex?
Wouldn't it be not QMA-hard if that were the case? Like, how could it be QMA-hard? Like
there.
Oh, you mean like, okay, so if the original Hamiltonian that you're talking about is like constant size, then clearly it's not QMA-hard because you can just like say all of the ground state, like say all of the product components individually. Classically, that would be an MP. This is like the Brandauer argument. If you're saying like, will the, like if you start with some like already large Hamiltonian with like possibly large entangled ground state and then like take a tensor product.
Yeah, I think that's what he's saying. Okay, I think he's not saying that like the ground state is like product across the qubits.
Okay.
He's saying if you had a full like gap amplification reduction from local Hamiltonians to local Hamiltonians,
which has like the
witnesses by tensoring the witnesses.
There's the question about, but the question's about whether the ground state is going to be tensor product or such.
Yeah, but tensor product across like groups of n qubits.
I think not. I mean, here even it's not clear it is, right? Like here only we say it's like tensor enough that we get this variance bound. It doesn't mean that the actual ground state is product, and I don't know if it is. So I would say no.
Yeah, please.
First of all, thanks for the great talk.
And I really like the fact that you mentioned the term quantum variable. That's up. I have two questions. The first one, you were talking about constraints, about quantum blocks. This screams to me like could somehow be used Montanato's backtracking algorithm or branch bound, because that might be some kind useful here. But that's not actually a question. When you were doing the projections, you said that there's like a low percent probability of success. Could you then enhance this probability by the means of amplitude amplification or oblivious amplitude amplification or repeat the success procedures, or is there a way to increase the probability that you said that it's minuscule?
Which probability is minuscule?
I just took notes and you said that these things are, there's a low probability of this happening when you were having the rectangles next to each other. Yeah, I took a note. I forgot what it was tied to, but
Rectangles. This one?
yes, I think you said something about probability of success, and this again made me think of amplitude amplification or increase this probability of success.
So some of the projections that the projected constraints, some of them not having high probability of like outputting yes, that's a feature that you want, right? Otherwise, otherwise it would be a satisfiable Hamiltonian, right? So.
Okay, yeah. So just following up on like Chinmay/Anand's question, so it won't be a product state, but it will be exchangeable just by symmetry. And is it correct to sort of think of what you're doing as sampling with pairwise independent things so that it's exchangeable enough that you can carry through this argument?
Right. Yeah. So it's not actually like, I don't know if it's actually permutation invariant. Like we don't. Okay, in this particular case, t is a constant, so we could make it permutation invariant if we wanted, just by like manually like adding in all of the permuted constraints, right?
No, if you did do the full tensor product, it would be right. But
oh, of course,
you can't afford it, so you're seeing some pairwise independent.
Yes. So the question is, okay, the full tensor product is going to be exchangeable. Yeah, the full tensor product is easy to analyze because the product, like the ground state, is a product, right? And yeah, I guess you could view the proof as just saying like if you pairwise independently sample the terms instead of having all of them, the state becomes sort of product enough or exchangeable enough that you can carry out the analysis.
Yeah. Okay. Yes.
Yes. What exactly would be the sparse PCP?
What exactly would be
the so what would be the statement for that?
Oh,
so I feel like at some point I convinced myself that like just a sparse Hamiltonian with a gap is sort of, you get the, like a constant gap for sparse Hamiltonian would be QMA-hard. But maybe you had a different statement.
Maybe like okay, so the statement is all the same conditions as the PCP theorem, except instead of requiring each term to be local, you require it to be sparse. So the matrix in some fixed basis for all terms has to have polynomially many non-zero entries in rows and columns. It could be that it's just true. Like,
so you're just replacing locality with k-locality.
Is that the case? Like locality and sparseness, like locality implies sparseness, but not the other way, right?
Well, if it's sparse on a certain basis, can I use that basis to like rearrange my tensor factors? Yeah, maybe it's not obvious.
No, I don't think it's obvious because like, okay, the sparseness could be unstructured, right? You can just have a giant matrix and it just happens to have like, only polynomially many non-zero entries. Like one way to see it's very different, I think also Anurag had this observation, is like, you cannot compute, like we know that the cat state is not the ground state, a unique ground state of any local Hamiltonian, right? But so that's because you cannot compute like ANDs, like you cannot compute large fan out gates locally, but you can do that sparse in the sparseness.
Okay, so I'm gonna ask a very quick last question and then we'll finish up. So have you thought about applying these techniques to area laws, maybe even reproving area laws? Because I mean, you're kind of saving a lot of terms. So the Hamiltonian has bounded norm, gap amplification is like speckle gap preservation. So I mean, have you thought about it?
I have not thought about that, but you're the expert, so.
Okay, so with that, let's thank you for it. We'll be back after lunch. at 2 o'clock.
Oh, no. I would recommend.
I actually don't know how to.